All right, so the second part of Indiana 3, we're going to be dealing with complementary probabilities. And we're going to be talking about example 4, which is mutually exclusive events. Okay, and those are two totally new concepts that we haven't done yet. So the first thing is example 3. It says find the complement of an event. I think once I explain it, we're going to go away from the workbook for a second. We're just going to talk for a second. I think you'll understand what I mean by a compliment. So there's two ways you can use the word compliment. I could say, wow, your hair looks great today, right? That's a compliment. That's not what they mean here. What they mean here is, what is something that makes you whole? That's your compliment. So let's say you and your friend have a dollar bill and you rip it, right? If your friend has 3/4 of that dollar bill, and you have 1/4 of that dollar bill, you have your friend's complement. You have the part of the dollar bill that your friend needs to add to their part to make one whole dollar bill. Okay, that's what they mean here by a complement, is what fraction do I need to add to another fraction to make it whole? So if I ask you, what is the complement of 3/4, what makes that a whole? 1/4, because 3/4 plus 1/4 gives you 4/4, which is a whole, right? One whole. Even though it's 4/4, we know that reduces to 1. If I was to ask you, what's the complement of 3/8? 5/8, because 3/8 plus 5/8 gives you 8/8, and that is a whole. We good? Okay. So that's what it means here by a complement. So if you know that you're looking for something and its complement is 1/8, you know that what you're looking for is 7/8, because it's the complement. It's what it takes to make it whole. So now let's take that into probabilities. The word I want you to underline here, the really important thing I want you to notice, is this word not. This is something we have not done before. Now, instead of looking for events that happened, we're now looking for events that not happened, okay? But to find those, we kind of have to circle back to what we've already learned. And here's what I mean. When you see the word not, okay, I want you to pay attention to what comes after that word. So this says, what is the probability that a coin tossed 3 times will not land tails up 3 times? To find the not, I'm going to concentrate on what I highlighted in blue. I'm going to ignore the not for just a second. I'm going to act like the not's not there. Say that 5 times fast. I'm going to act like the not is not there, and I'm just going to focus on what came after the not. And I'm going to find the probability of landing tails up all 3 times. And we can do this, right? This is easy peasy. We've done this already. Coin 1. Nope, let's get a pen. That makes it easy peasy. There we go. Coin 1. Landing, what do I want? Tails? Yeah. Coin 1, landing tails up. What's my probability of that happening? 1/2. Coin 2, landing tails up. What's my probability of that happening? 1/2. Coin 3, landing tails up. What's my probability? All right. So to find compound probability, what is 1/2 times 1/2 times 1/2? 1/8. All right. So the probability of this part right here happening is 1/8, but I want to know what's the probability of that not happening. So I want the complement of 1/8. So if I take the whole 1, which is what they've done here, minus what I just found as the complement, which is minus 1/8, I get 7/8. Now, when you see that 1, how could I rewrite that 1 to make it easy to subtract? 8/8. Okay, I can make it 8/8 because that equals 1. And now I found that the complement, or what the other half of my not, I found to be 1/8. If I find the complement of that, or I subtract that from 1, I get the not answer. So this right here, this is the answer to the not question. But to answer a not question, you have to first find the probability of it happening and then find its complement or subtract it from 1. Does that make sense? there was something else. Oh yeah. If you have a fraction that the denominator, if you found your complement and the denominator is a 12, how could you rewrite your 1 to make it easy? 12 over 12. If your complement has a denominator of 6, how could you write your 1? 6 over 6. So now you guys kind of got what I'm talking about. So you can rewrite the number 1 as whatever fraction you need to make it easier to subtract. Okay, so let's try it. Okay, it says Casey will toss 2 coins. The first part of the question is actually, it's kind of helping you. It's finding your complement first. It says, what is the probability of 2 coins landing heads up? Right, that's the first half. Then it goes on to ask, what is the probability of the 2 coins not landing heads up? Right, there's that not word. Well, we can't do the not problem first, right? Because you can't find the not until you find the opposite of that. So let's do the blue highlighted portion first. It says, what is the probability of 2 coins landing heads up? So coin 1 landing heads up, coin 2 landing heads up. That was weird. All right, what's the probability of coin 1 landing heads up? Probability of coin 2 landing heads up. Okay, we multiply that and we get 1/4. So the probability of it happening is 1/4. So now to find the probability of it not happening, I would subtract that 1/4 from a whole to get the complement of what makes 1/4 whole. And again, if you want to, you could rewrite that 1 as a what? 4 over 4. So what is the probability of it not happening? 3/4. So that 3/4 is the answer to the not portion of it. Okay, so there is an extra step. If you're asked the probability of something not happening, you have to find the probability of it happening and then subtract that from 1. Okay? All right, very good. Now we're going to move on to example 4. So turn the page to Indiana 16. And please make sure you're at the top of the page. Earlier today, I had people on example 5 when I was on example 4 because they look so much alike. So just be very mindful that you are on example 4. And I want you to take a minute over here where I've got mine to write the steps. So everybody right now should be writing. I'll zoom in on it here. Everybody should be adding this right here to their notebook. And where it says find P of each event, what does that P stand for? Thank you. You guys are awesome. I just was using shorthand. Raise your hand if you need a second. Everybody's good? Okay. What is different here that you notice is different than what we've done in the past with 2 probabilities? What's step 3 telling us to do? What have we done in the past to probabilities? We multiplied them. I'm going to show you how to know when you multiply, which is what we've done so far, and when you add, okay? Think back to every problem we have done so far in this week. We've done roll a 6 and flip ahead. We've done spin a spinner and get a blue and flip a tail, right? We've done draw a blue card and draw a 3 card. Everything has been and. Notice here, when we go into these mutually exclusive events or these special kind of events here, what is different? That word or. Okay, when you see, and you're going to write this on your paper, everybody is, when you see the word or, you need to think add. Okay, and if you want to give yourself just a little reminder, this is a review. When you see the word and, you need to think what? Multiply. Everything we have done so far this week has been and problems, right? Flip a coin and roll a dice. Now we're getting into OR problems, and you do them differently. And there are two kinds of OR problems. Example 4 is called a mutually exclusive event. Example 5 is also an OR problem. You'll see it right here. Example 5 is also an OR problem, but it's not a mutually exclusive event. So when you get an AND problem, you don't have to think about what kind of event it is. It's just a compound event, because AND means two things happening. That's compound. When you see an OR problem, you do have to ask yourself, before you work it, you have to ask yourself, is this a mutually exclusive or not mutually exclusive OR problem? Okay, because there are two different kinds, and I'm going to show you how to tell the difference. All right. The main thing to remember, or the main thing I want you to get right this second, is that when you see the word OR, it's add, and that is different. Okay, that's different than what we've been doing so far. All right, so let's look at our problem. It says Shannon will roll 2 number cubes numbered 1 to 6. What is the probability of the sum? Now, I do want to point this out. Underline this word sum. This is not a typical table that we have done so far. So far, our tables have just been, you roll a 1 and you get a head, and so you put 1H in the table. This is a sum table. With a sum table, it's if you roll a 1 and you roll a 1, what do you put in the, where they meet? You put the sum, you put 2, right? You roll a 1 and you roll a 6, the sum is 7. You roll a 6 and you roll a 6, the sum is 12. So a sum table is different, and you got to be mindful of that when you're creating these tables, that if it's a sum table, you actually have to do some addition to fill in the table. Okay, so that's the one thing, is that it's a sum table. Then it says, okay, it says, what is the probability of the sum of the numbers rolled either is even, that's one option, or, so that tells us we're going to add, not multiply, or equals 11. Now, here's how you decide, is this a mutually exclusive event or not? Can you have a sum that is both even and 11? Is 11 an even number? So can you have an overlap of an even number and the number 11? Okay, so this is an example of a mutually exclusive event. There's one less step to do with these. These are nice. The ones that the next example we're going to do, where they're not mutually exclusive, there's a second step. So that's why these are kind of easier to do. So when you have OR problems and you have them that are mutually exclusive, meaning you can't have overlap, you can't have an even number that also equals 11, okay? The first thing you do, you have to take it one bite at a time. First thing we have to do is right here. We have to find the probability of an even sum. So they already have them highlighted in red, but you guys are still going to do it because you know I want you to do it in your tables. I want you guys all to go through your table, and I want you to circle every even sum. Okay? And like I said, they're already highlighted in red on this example because the examples are already done for us. But we're still going to do this. We're going to go through and we're going to circle every even sum. And then we're going to count up how many we circled, right? What is the probability of getting an even number? Well, it's 18 over 36, and they reduced it to 9 over 18. That's fine too. Okay. Then you're going to look at the other half of the OR, which is equals 11. So now we're going to go back to our table, and we're going to circle the ones that equal 11. And notice there's no overlap. We don't have anything already circled blue that we now circle purple, right? They're mutually exclusive. There's no overlap. So now in a separate transaction, we're going to come right here and we're going to find the probability of a sum that equals 11. And there's only 2 instances, or 2 times I circled that happening. So the favorable event of it equaling 11, there's only 2 of them. So then we're going to build the probability 2 out of 36. And then they reduced it to 1 over 18. Now, I want to ask you a question. Why did they not reduce this one right here? Because this one still is reducible, right? But they didn't reduce it to 1 over 2. How come? Yeah, they thought ahead that here in a minute, I'm going to have to add this number and this number. And I don't want to add 1/2 to 1/18 over 18. I can't. So I'd have to back up to 9/18 anyway. Here's my suggestion. I wouldn't even reduce at all. Me personally, I wouldn't have even done this step. Because if you know you leave it 18/36 and 2/36, do you know you're going to have a like denominator? So adding is very easy. Now I'm going to show you both ways, and you get the same answer either way, but I just want to show you why they didn't reduce 9/18 again. Okay. So I kind of lost track. I was looking at the clock and I lost track of lost my train of thought. So what they've done now is they've added, right? Let me highlight this in the color I've done it. Here is the probability of us even, and they've put it here. Here is the probability that they found of a sum of 11, and they've put it here. And they added them together, and they got 10/18, and then always reduce if you can. So the final answer here is 5/9. Now I want to show you, what if I didn't reduce at all? And what if I did this 18/36? And what if I used that 18/36 plus, what's my other one? 2/36, 2/36. I would have gotten 20/36. If I reduce these, they're both divisible by 4. What do I get? 5/9. What did they get? 5/9. So you can reduce it as much as you want, but don't reduce it so much that you force yourself to not have common denominators, because then you're going to have to unreduce, and it just makes a little bit of extra work. Okay. So as a little bit of a recap, okay, when you see the word or, you know you're going to add, not multiply. And when you see the word or, you've got to make yourself stop and think, mutually exclusive or not mutually exclusive. Okay. And in this case, they were mutually exclusive, meaning they could not both happen at the same time, because we can't have an even or an 11, right? Now, what if it had been even numbers or equaling 12? Could we have had some overlap there? Could we have even numbers that do equal 12? So that's going to be like example 5 that we're going to talk about tomorrow. Okay. So, and this is just my wording of it, where it says here mutually exclusive. It just means can't both happen. That's what it means when it tells you that something is mutually exclusive. We can't be even and we can't be 11 at the same time, right? Those two are mutually exclusive. All right. Sound good? So tomorrow, the plan is tomorrow we're going to go over example 5. Example 5 is another or problem, which means, are we going to multiply or add our probabilities? We're going to add them, but tomorrow is going to be an example of not mutually exclusive, and that just tacks on one little extra step at the end. And then we'll kind of talk about how that compares to example 4. And then in class tomorrow, we're going to do one quick example, which is example 5. That finishes up our notes. Then in class tomorrow, you guys are going to have the whole class time with me in here to work on your homework, so that I'm here to help, because this is a little bit of a challenging section. So I want to make sure that I'm here when you do your homework to help you. So that means, guess what for tonight? No homework. Enjoy a night off. All right.